So welcome to Natural Computation and Self-Organization. So this is a physics graduate class, and we're going to talk about computation in the natural world, pattern, structure, organization, chaos, irregularity, many different things. What I'd like to do today is, for the first half, motivate the class, what the big issues are. I would like to argue that this is sort of an unusual class in that we're not focused on a particular technical topic like studying differential equations or general relativity, but in fact the course over the winter and spring quarters tries to give you a picture of almost the whole sort of arch of scientific practice. So I'll try to motivate that a bit today. And then the second half will be a discussion about logistics. This course is different for me this year in that we're going to run it in a flipped format, so that, unlike today, so I'm recording the video lectures here. Actually, could you sit over there? Is that okay? Thanks for that reason. And so the lectures are all online, which is, I recorded them last year. And we're going to use the class time to work on problems together. Now, another unusual thing about the course, and I'll get into some detail about this, is that all of the homeworks, exams, everything are online, and you do them through a browser. There's a system called Sage. You might think of it, it's sort of like Mathematica or MATLAB, but in a browser. And we do all of our programming in Python, but the homeworks will have helper code. So this is not a programming course, but it will involve a little bit of coding. So hopefully you have some experience with that. And if you don't, the benefit of this flipped format is that the classes are going to be working through interactive labs, showing you how to program, working through homework problems and solutions. And we have a number of different, my graduate students and postdocs will be helping us with that. So this is all new to me. This format this year, this so-called flipped format, will be new, and it's an experiment. It took me 3 or 4 months to convince myself I should do this. I'm kind of an old guard, like to stand up in front and pontificate at a lecture, but now they're all online, so why do that? So I'm kind of hoping that then through the flip format I'll get to know how you're thinking about the course and the material much more directly and much more one-on-one. Okay, so that's what we'll do today. First, sort of philosophical and scientific intellectual motivations for the course to try to give you, kind of justify this unusual course, where we're not going to go into particular topics in a lot of depth. I want to nonetheless put topics in a series so we can sort of see maybe a picture of what modern scientific inference is. How do we build theories of the world? How do we come to understand the world? So the sort of largest context for thinking about the course takes us back to the Industrial Revolution. So in the late 1700s, sort of through the 1800s, human beings, us curious little animals on this planet, went through a major change in how we lived our lives because we figured out how to harness unbelievably large amounts of energy through things called steam engines or heat engines. And we sit here today with video projectors and computers in a nice warm room, being the primary beneficiaries of this revolution. And these so-called engines were devices that humans had invented that could convert thermal energy, abundant thermal energy, into useful work. And this manifestly changed how human beings lived. Much of the world we live in now, both positive and negative, is a consequence of this. Right? We're harnessing all these material resources through commandeering energy that allows us to be comfortable and live like kings did 500 years ago individually, but we're also able to change and modify, pollute, and maybe even improve the environment we live in. So these changes, these massive changes, come with both positive aspects and negative aspects of them. What's interesting from a scientific point of view is that as this Industrial Revolution unfolded, it wasn't like there was a central theorist or mathematician or physicist who wrote down the theory of how you can convert thermal disorganized heat energy into work, organized energy. It was this very interesting interplay between basically inventors, entrepreneurs, engineers, and more theoretically oriented people that we have come these days to call physicists. It wasn't as if this idea of an industrial revolution sprung out of the head of one person. There wasn't a Newton that said that this was possible. It was very much an interplay between thinking about the mechanisms, how heat engines, steam engines worked, and having difficulty making them, say, more efficient. So there's this very close historical dance between engineering and science. It's not really so unusual today. So there was, of course, then eventually through a number of physical scientists, natural philosophers, the sort of science of thermodynamics was developed, and it continues to be one of the most important parts as articulated in what we call statistical physics or statistical mechanics today. Understanding how heat engines worked and what their thermodynamic and energy conversion efficiencies were. So that's a kind of historical setting. Okay, fine. Major change in society. Eventually science catches up. We have first principle understanding of what's behind these engines that convert thermal energy into useful work. Eventually the science gets so well developed we can greatly improve the efficiency of these machines that we're building. Great, okay. And again, we're all benefiting from probably 150 years worth of hard work trying to understand that. And it goes on till today, of course. Well, at least in popular culture today, where you sort of hear that we live in this information age. And, that ranges from phones to computers to the net, video projectors, all these different ways we have of communicating. And the question that I want to pose to you is, what's the corresponding theoretical underpinnings of all this information technology, how it's changing our lives? Some people argue that what we're going through, this information age, is as transformative, maybe not in a raw energetic sense, but maybe in an intellectual sense, in a social organization sense, as the Industrial Revolution was. And we know from this history that eventually, through interaction between mathematics and the experiments, we came up with a corresponding theory of heat engines. So now my question is, where's the physics of, what's the analog of thermodynamics in the modern age for information? So that's the kind of main historical philosophical question the course is oriented towards answering. What tools do we have to answer this question? Well, physics, okay. And if you'll excuse me to be a little bit kind of crude here, one way to think about physics is that so far, and what you've learned in your physics classes, is physics is a kind of energy bookkeeping, right? We learned that there are certain kinds of energy. There's gravitational potential energy, and if I were to drop this, you can convert it to kinetic energy, chemical energy, thermal energy I already referred to. So there are different kinds of energy, and they're stored in different ways. And there are different ways of transducing these different kinds of energy. And that's this kind of very crude picture of what physics is about. Where's the energy? What's storing it? And how does it get transduced from one form to another? So what's this physics of information? We can sort of ask the same questions. What is information? What kinds of information are there? What things store information? And how do we transform information? Different kinds. So those are the sort of concrete questions we'll be addressing. Now you might wonder if there isn't some relationship between this, in some sense, more familiar concept from physics, energy, and information. Well, as we start to investigate what information is, we should also keep in mind the history of this. Just, 300 years ago, there were major debates over whether energy depended on the velocity of a mass or the velocity squared. And we take that for granted now, that we have momentum and kinetic energy. But there were serious debates about that. And I think that's kind of the right way to think about where we are with discussing what information is. I'm going to try to convince you it's not a unitary thing. There are different forms of it. But I would say in terms of the maturity of answering this question, we're kind of in an analogous state. Should it be v or v squared? Well, okay, let's see what works. And of course, the answer back then was both momentum and kinetic energy are useful quantities. So we'll have the same sort of criteria for, as we introduce information, different kinds of information, what works, you know, will be kind of practical, what's useful, what helps us describe the world around us informationally. Now, it's generally a good idea if you're trying to understand something to not unnecessarily conflate it with another thing. So I'm going to start off with assuming that information is not energy. There are some quarters, there's some areas in this general set of questions where people actually think these things are equivalent. But let's wait and see if we can convince ourselves of what the relationship is. So we'll start off assuming that information is not energy. And I'd like to kind of make an argument, qualitative argument for you that information is not energy. So in particular, let's think about the role of information in a causal chain. So there was some initial energy of the gear rolling.
Isn't it nice when things just work?
So you'll have to excuse me for the product placement, but I like this particular one. The actual conceit of this series of contingent events actually goes back to some Dutch artists that have a nice short film called The Way Things Work. And this is a modern remake of that is particularly nicely done. Okay, so what did we just see? Well, think back to the very beginning. There was some rotational kinetic energy of that gear, okay? Certain amount of energy, some number of ergs, okay? But we had a series of these triggering events. In fact, there's basically about 40 different events in that whole chain. Now imagine that each one of these events transfers its energy to the next stage with only 10% efficiency. So you can ask the question, how much of that initial kinetic energy of the gear rolling down the inclined plane was responsible for the 4,000-pound car rolling off the ramp? Well, 10% efficient, 40 interactions, only 1/10 of the energy is going through, the amount of initial kinetic energy that's left over was 10 to the minus 40. And in fact, a lot of those conversions are 1 part in 100 efficient. So the point is, and you can make that chain longer and longer, the initial energy is essentially not present in the final macroscopic effect, this giant car rolling off the ramp. So what kind of story are we going to tell? Is this an energy story? Well, presumably we could, if we paid attention in our physics classes, you could go through each interaction and analyze it. So pick one. There's a funny one. There's a ramp with tires on it. Something hits the tire that's low down on the ramp and it rolls up. It hits another tire that rolls further up, further up. Okay, so how could that happen? Well, obviously, this entire chain, every stage of the chain is set up. So what's happening, of course, is the tires have an offset weight. And they're prepared. There's stored energy there. And so there is an energy story you can make about this, but it's really this contingency and sort of amplifying very small perturbations at every stage that become manifest macroscopically and carried by some energy, but then go to the next stage, which is poised and ready to release energy again. So I claim that's more of an information story in the sense we're going to develop the concept than an energy story. I'm not saying that energy is not involved, but it's arbitrarily weak. There's this macroscopic chain of events, gear rolling, car rolling off the ramp. That's more of an informational story we should use. So we'll be studying systems like this that have they're poised. They're sort of ready to react to even arbitrarily small stimulus. And we'll develop a way of thinking about the energetics of it, but mostly how do we talk about these sort of causal change and contingency in terms of information. Now, a key thing in the story we're going to tell is that it's a deeply mechanistic story. There's been, certainly in the last 50 years, very active, but the ideas that we're going to develop go back a century to the French mathematician Poincaré, who was studying this problem called the three-body problem, Sun, Earth, and a massless moon, and trying to understand why, the astronomical observations of the stability of the solar system should hold. And he developed this notion that even simple mechanical systems like that three-body problem have inherent instabilities built into them. So today we call this deterministic chaos. And that's going to be a topic that we're going to focus on in the first third of the course, is mechanisms that produce unpredictability, how instability can actually be shaped and molded to various purposes. And the conclusion is going to be that through these instabilities, nature actively produces information. That information, surprise, randomness don't come from our ignorance. They can, but there are mechanisms in nature that actively amplify small-scale fluctuations to macroscopic phenomena, pretty much as we saw in that chain. So this will set us up so we can start talking about some of these issues, which you might think are kind of philosophical. What is randomness? Where does it come from? But in very concrete mathematical and physical terms. And there's sort of a flip side to this too. Now that this area of deterministic chaos and the mechanisms involved are now well understood, that kind of begs the question, why isn't the entire world around us unpredictable and chaotic, some ideal gas? In fact, the world around us is quite organized. So as soon as you start trying to understand how the world is intrinsically unpredictable and chaotic, random, you have to ask yourself the question, why isn't everything random? How is it that, well, I'm over here and you're over there, so already the world is kind of ordered, right? And I'm using things like language to talk to you. I'm not just screaming, random noise at you. There's organization and structure in the world. So we're going to move on from trying to analyze how unpredictably arises in the world to talk about organization and pattern and how it emerges, what we call self-organization. That on the flip side, in addition to nature actively producing randomness and being unpredictable, it also actively produces structure, organization. And again, we have to start to answer the question, what is structure, what is regularity, what is order, pattern, and so on. And we're going to need some metrics for that, some nice concrete mathematical definitions for both what randomness and unpredictability are, but also what order and regularity are. Are these the same thing? Is order one minus disorder? That's a question. A lot of people think that's true. I'm going to argue that they're actually complementary. So where does order come from? And there are lots of examples, just to kind of give you some visual examples of order. Kind of favorite examples here. This is chemical reaction. We're looking down at a petri dish here with 5 different reagents. This is called the Belousov-Zhabotinsky reaction, invented in the late 40s. Took the Belousov and Zhabotinsky, these Russian chemists, about 10 years to get it published because the editors of the chemistry journals thought that the formation of these dynamic spiral waves violated the second law of thermodynamics. It should have been just brown goo, disorganized. This small picture here, this is a series of 4 fluid flow experiments with the velocity moving past the cylinder going from left to right, and you go down the different experiments, the velocity goes faster and faster, and what you see is that there's this increasingly large amplitude instability, and you end up with these pairs of vortices, the so-called von Karman vortex street. Very organized. This looks like a plant vascular system. In fact, this is what happens when you put a piece of plastic under stress and it cracks. You get these channels of sort of statistical self-similar distribution. This is a petri dish again, but now with bacteria, and some evil biologists have put some nasty toluene in here, and the bacteria get together and sort of run away from the nasty chemical together. Stripes in the zebras are used by ponies to find their mom. So there's patterns all over the place. Obviously spontaneously generated. The question is how, what mechanisms produce that? And in particular, if we're talking about what is randomness on one hand, and then how is that related or not to pattern and structure and order, how do natural processes balance the two things? Every system we have is presumably in some heat bath, so there's already some stochasticity in there. And how does natural mechanism balance a tendency to be ordered and patterned versus just amplifying sheer randomness? So we'll study some systems where we can talk about the balance between these two things. And then these issues also bring up kind of, in fact, the entire discussion I'm making here, it kind of begs the question, how do we find patterns in the first place? So we're all kind of familiar with what is called, there's a technology called pattern recognition, right? You call up American Airlines and it's the machine you're talking to says, where do you want to go? And you say, Chicago, or I guess probably not today. And what the machine has done, of course, is ask a question to try to narrow the range of your responses. If you respond chair, it's not going to understand. But if you say Chicago or Miami, Miami is probably more plausible today, then what happens is that frequency utterance, the utterance you've made gets analyzed in terms of frequency components and matched against a set of phonemes and word templates that a speech engineer has painstakingly put together. And then the machine just matches against the actual utterance you made and the templates and does a statistical estimate of what the closest match is, and then that's the word Chicago that you said. At least that's so. But that begs the question of what the patterns are, what these phonemes or words are. What we're talking about here is pattern, what I call pattern discovery. How do we discover patterns we haven't seen before? We'll be studying self-organizing systems where we can write down the equations of motion, but we don't know what the large-scale emergent structures are going to be. We have to go out and discover these new patterns. So pattern discovery is, in a sense, trying to ask the question, how do we extend our vocabulary to understand new things? And hopefully this will be sort of a metaphor for the course. You didn't walk in the door because you knew exactly what I was going to say, right? Otherwise, you just wouldn't show up, right? Because you already got it. On the other hand, and I'll have to be careful if I race ahead too fast with concepts, or if I start speaking in a foreign language you didn't know, that would be too much information, too unpredictable, but it wouldn't be understandable. There's some sort of balance in human communication between sharing of vocabulary and syntax and my telling you something novel, but not so novel that you can't understand it. So even language systems have built in this notion of allowing communicating agents to discover sort of new ideas, new patterns. And this, of course, will bear directly on why do we build models? What's a good causal explanation for a system? Right? We're going to be studying these nonlinear, chaotic, self-organizing systems, and we're not going to know a priori how they organize. They will form patterns we don't know about, so we have to understand what it means to discover new things. Hopefully we'll be able to do that. I mean, my claim is that human beings do this all the time. Scientists, what we're trained to do is actually discover new patterns, not just recognize familiar ones. Okay, so I'm just throwing some questions out there. These are the things we're going to try to address. Hopefully, as we go through the course, you can think back to these general issues. We will definitely be down in the theoretical and programming weeds at some point, but everything we're doing is motivated by these larger issues. And I hope you'll see that there is a way to think constructively about these questions and to answer them, even quantitatively. Okay, so now sort of more of what the kind of technical logic of the course is. It's really broken into 3 pieces. So the course is winter and spring. I really think of it as one course. And so the first third of it, we're going to study complex systems, complex, nonlinear, stochastic, dynamical systems to understand what it means for them to be unstable and produce unpredictable behavior, to be deterministically chaotic. Also, how they produce order. We'll look at pattern-forming systems and see how order can emerge, even in the midst of noise. Talk a little bit about emergence, namely properties that as the system relaxes, something becomes patterned or something becomes unpredictable. So we'll deal with this concept of emergence. And then finally, we're going to deal with this notion of computation in the natural world. Namely, try to figure out how nature stores and processes information. And so the main idea of the course, so this is the punchline, is that structure in the world is some combination of information storage and processing and computation. Now, what this means, to understand that phrase, what it means is we're going to have to relax our notions of what computing is to not be that happens on our iPhone or on our laptops or on our supercomputers. We have to take this much more agnostic view of what computing is. We have kind of a problem here. The information age, we're just awash in discrete symbol, discrete time computation. And therefore, we sort of conflate computing with these things. But there are many other systems in nature that store and process information. In fact, I often visit the Redwood Center for Theoretical Neuroscience down at Berkeley, and the argument I'm making doesn't need to be made down there, because the neurobiologists study a tissue whose purpose is to store and process information, namely brains, neural tissue. So somehow evolution, biological evolution, has produced this organ, a brain, or neural network, that stores and processes information. So that happens in nature isn't such a big deal. And although there's some interesting historical ironies about the way neuroscience looks at information processing these days, sometimes you'll find people really thinking about discrete computation as an appropriate metaphor. And the historical irony is that Alan Turing, the British mathematician that introduced the formal theory of computation, that is the model in which these machines are made, back when he was introducing this idea of discrete computation in the 30s, here's a paper that he wrote in 1939 that talks about computers, except in his day, computers were people that had a pad of paper and a pencil, and they put marks on a page. And based on this kind of metaphor, that's how he built his mathematical formalization of computing that we now use and that we engineer machines to meet. So the irony, of course, is that here we are thinking about brains that process information, and now we're using computers, digital computers, as the metaphor, when in fact computer originally meant humans. Anyway, some circular irony here. I love that. Or another way to summarize this idea, again, the main idea of the course is that how nature is structured, look out at the world, it's structured somehow, is how it computes. This is almost a kind of a tautology. I mean, it's, and so we're sort of going to develop a set of ideas so that this makes sense, that there are ways of, that natural processes, physical, chemical, biological systems, store, process, and generate information, compute in a general sense, and that's actually related to how they're structured. The symmetries, regularities, so on that they have. How they're structured mechanistically. Okay, so how are we going to do this? I mean, these should hopefully, these are tall claims. How are we going to do this? So again, drilling down again, sort of more practically, the outline of the course is 3 tools. We're going to study what's called dynamical systems theory, so the modern version of thinking about ordinary differential equations and partial differential equations, although we'll also do We'll do discrete time systems and stochastic processes too under this heading. Then once we study the mechanisms that produce order and randomness, then after a while, okay, I got the idea, things can be random, things can be ordered. You want to measure these things, you want to be objective about it. So we're going to borrow from the theory of information, introduced in the 1940s by Claude Shannon, mathematician at Bell Laboratories, telephone company. He was interested in information communication, reliable information communication. We're going to borrow and then pretty substantially extend his notions of information to start to address some of these issues. How random is a process? How random is a natural process? How structured is it? And then the final topic will be, we'll start to realize that information theory isn't quite enough, and then we have to introduce more directly what I call computation mechanics, a theory, an extension of statistical mechanics that deals with information processing and computation directly, that deals with structure, actually makes a mathematical commitment to what structure is in a process in the world. So, sort of studying the kind of rich phenomenology of the nonlinear stochastic world, and then how to quantify how unpredictable it is, that'll be the burden of this quarter. Then in spring, we're going to focus on pattern, structure, regularity, how to measure that. And also, we're going to recast everything we've done in the winter quarter in a new way. To get a very detailed picture of what kinds of information there are in the world, how they're transduced, so on. Now there's a graphical roadmap for the class, what I call the learning channel. And this is what I alluded to before when I said the course in a way is actually going to kind of go soup to nuts on how our sort of current picture of how science works. So here's the graphical picture here. We imagine we have some system in nature out there that has some states and some dynamics switching between states. But of course, we don't get to see all the detailed mechanism in detail. We have instruments that have limited accuracy, limited sampling frequencies, and so on. So this is kind of a gray box. We just get some measurements coming out here. So this is experiment, instrumentation. There are a lot of complicated issues here. How can I partition this into just binary or some larger alphabet? How often should I sample? How many probes should I put into my system? These are very practical issues. But eventually, we end up with a kind of time series of measurements. And then the issue is, what can we understand from that? From this impoverished, sort of inaccurate view of what's going on in the box, how much of the internal dynamics and states can we reconstruct, pull out of the impoverished data, and then build some kind of model? So, winter quarter, we're going to talk about how rich the box can be. What kinds of models are there? What kinds of processes are there? Then we're going to study what the alternatives are to instrument something, come up with a way of characterizing good instruments and bad instruments. I mean, a bad instrument just returns all zeros, right? And there's no reason to even think you should be able to construct a model of what's going on inside of your instrument. Just put out all zeros all the time. So there's some kind of trade-off. Well, we're also going to see that there's sometimes ways of instrumenting a system that actually add complexity and structure that's actually misleading. And we have to understand that. Then we now have this sort of data stream coming out. What can you extract from it? How much information does it contain? What kinds of information does it contain? What are the correlations between the measurements and so on? And then finally, in the spring quarter, we'll be talking about what's a natural model of a process. I mean, it's one thing to go from data and measure some statistic like the average temperature or velocity. We're going to be asking a much more challenging question. Does the data stream tell you how it should be represented? Now, part of the courses you've been taking, right, if you paid attention to physics, first, one of the things you learn about are Fourier transforms, looking at a system in terms of the frequency domain. But when you take a time series of measurements and you take the Fourier transform of it, you're bringing to the understanding of that process a big assumption, namely that frequencies are the right representational basis. And sometimes that works. If it's a periodic signal, hooray. If it's not, you'll get an answer out. In fact, that's kind of the universal property of any statistical analysis. You'll get an answer, but what does it tell you, right? And so we're going to kind of lay out a framework where we can start to see that as we choose instruments and choose representations, it can color the kinds of structure, or even how well we can estimate the randomness of a process is colored by the assumptions we bring, the representational assumptions. But the spring quarter turns on a really important idea, namely that there is a natural intrinsic representation. There is a way of going from impoverished data and building the best model you can from the given data. This is kind of a natural inherent representation. And yeah.
So with this, I guess, framework, are you saying that since all instruments have limits, it's almost impossible to actually accurately model any natural system?
That's an excellent question. The facts of the matter are much more optimistic. In fact, there are ideal instruments, even ideal binary instruments, so that you can just look at a binary string coming out of a nonlinear system and reconstruct the internal dynamic, the effective states of the process. So we'll study that in detail. As soon as we define that instrument, we'll know exactly how to do it wrong too, right? Because it won't have these properties that we define. It's called the generating partition. So yeah, so the interesting thing about this, especially with some of these chaotic, unpredictable systems, because they produce information, it means the measurements are very informative, and we can use even very coarse measurements to infer what the internal state and structure is. So that's yeah, there's a couple very subtle and interesting ideas in this. And that's one of them, that actually you can do remarkably well at modeling, even with extremely coarse resolution. Okay, well, let's imagine that we're actually successful in this, and you start to get some of these ideas. So my goals for you are that, by the end of the course, you'll be able to quantify unpredictability. You'll know how to measure in quantitative terms how random something is. Even if you go out on a cold morning, you put your key in the ignition and you turn the engine over, goes whoa, 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 and your engine's cold and idles roughly, you should think, oh, how unpredictable is it? Or more technically, what's its entropy rate? This I would love if that's the way you start thinking. Also, looking out at the world, asking how structured things are, and having at least in the back of your mind that you could measure how structured something is. So last year we had a professor from the design department studying the formation of tendrils in passion flower vines. And we came up with a measure of how these coiling vines, which are actually important because they kind of knit themselves together and make this nice sturdy wall, a plant. She actually learned how to quantify plants in her garden. And finally, to understand how unpredictability and structure are related to this information processing, this intrinsic or natural computing. So those are the goals. And we'll talk about a number of applications. So probably mid-spring quarter, we'll have enough of this background and vocabulary, modeling techniques, information theory, ways of measuring structure, that we can start thinking about various kinds of applications. And I just mentioned one, Christina's passion flower coils. There are other kinds of system that store and process information, and these can become the basis for the projects. The various kinds of novel computation, you probably heard, at least in the popular press, people very concerned about the digital CMOS technologies that go into building our today's computers, basically not speeding up and kind of reaching a roadblock. So people are now looking at quantum systems, computers whose basic logic gates are not binary Boolean logic, but are based on quantum operations and things called the quantum analog of an information unit is called a qubit. And of course, I already talked about neurobiological processes as storing and processing information. People have done various kinds of computing with DNA sequences using genetic manipulation. Continuous computation doesn't have to be discrete and Boolean, and so on. Computation with molecules, even atoms. We'll maybe talk about that. Also in nanotechnology, we're starting up a very large project at the center here on looking at information processing in molecules down at the nanoscale side. Other kinds of applications, studying the biology of living systems. One of the things that distinguishes biological systems from systems you study in physics, typically in chemistry, is that biological organisms often do things. That's referred to as function. They have function. And usually in physics, we don't think about systems having function, unless it's something material we've handed off to our engineering friends that want to design something. So there are interesting questions about how the structure of an organism is related to how it functions, and we can start to discuss this in the context of evolutionary dynamics, using some of these ideas of natural computation. Or, if you're a big fan of big data these days, a lot of these issues, like does data tell me how it should be represented most naturally and usefully, immediately bear on automated scientific inference. So, is it possible to build a theory of theory building? How do we do this? Do we understand what pattern and structure and randomness are in the world well enough, precisely enough, that, for example, we could teach a machine to do it, to build our theories? So I call that artificial science, kind of a play on artificial intelligence, which artificial intelligence was a disaster, but artificial science still has a possibility of happening. Some people are trying to do that. Okay, so these are some of the ideas. We have a long way to go to deal with all of these things. So now let me shift a little bit to talk about some of just the practicalities and the sort of different format of the course. So I'm a professor here in the physics department. I arrived about 10 years ago from this place called the Santa Fe Institute in northern central New Mexico. It's a small little private research center out there, and I've spent about 10 years there sort of developing a lot of the ideas we're going to talk about here, this computational mechanics and information theory ideas. Before that, I was at Berkeley for about 15 years in the physics department there, and before that at Santa Cruz as an undergrad, so I'm mostly kind of a UC brat, but I'm back here and enjoying it a lot. So we have at our Complexity Sciences Center a number of grad students and postdocs, and two of them have sort of volunteered to be teaching assistants, and they'll be involved in this flipped format I'll describe in just a second. So the first is Dr. Corinna Burke, and she's sitting back there. And she is UC Davis Chancellor's Fellow here for 2 years now. A year and a half. She studies nonlinear dynamics and chaos, in particular looking at sort of nonlinear dynamics, classical nonlinear dynamics in single atoms. So maybe at some point she can describe some of that to us. And then grad student Alec Boyd, second year student, he'll be helping us work on some of the problems and working groups and so on. And I hope over the weeks we have to get to know sort of who you are, what your interests are. Hopefully in this flipped format, there'll be a lot more occasion for us to interact one-on-one and in groups. So I'll be kind of trying to figure out what your interests are and what your backgrounds are. In particular, because the ideas in the course are so general, it's quite possible, it's happened year after year, where this actually affects how someone's doing their dissertation work. So it's readily adaptable. There are a number of interesting dissertation level projects that will come up in the course, but also it can come back and affect and hopefully change the way you're thinking about your graduate research. And there's a little bit of kind of a trade-off. We all have different talents. So in terms of abilities, some people like to calculate, some people like to program, so there are different kinds of things. So over time, I'd like to get some sense of the style of work you'd like to pursue. Now, this is probably the most important practical slide of the entire bunch, namely staying in touch. So the course is overwhelmingly online now. Okay, so the primary resource is the class homepage. You just go to my homepage, courses, NCASO, Natural Computation and Self-Organization. I actually, in my head, pronounce that acronym. There's a little town in Marin called Nicasio. It's near Skywalker Ranch where George Lucas lives. So I put an I here and an I here. That's Nicasio, but you don't have to do that, but that's the way I read it. Mail list. I hope everyone did anyone not get my email from yesterday? Good. Okay, make sure, see me afterwards. We'll make sure you get on the list. There's a page you can go subscribe yourself or unsubscribe for that matter. I took the list of people who had emailed me and also from the registrar's list, maybe on Saturday or Sunday, that was the list. So I'm using those email addresses, for example, that the registrar has for you, not your Gmail account, the UC Davis one, typically, okay? You can email me. I'm just chaos@UC Davis, or it's Karana, K. Burke, or Alec Boyd, A. Boyd at UC Davis. Office hours on Wednesday. I'll say this for the Berkeley folks. I'll be down there on Friday at the Redwood Center for Theoretical Neuroscience. Office hours 3 to 4 down there. Yeah, there's another 8 to 10 people that are taking this course remotely from Berkeley and UC Merced. So again, that's going to be a bit of an experiment. They don't get the benefit of these class meetings where we're going to be solving problems together, so I'm kind of curious. I'll put up the sort of office hours for Karana and Alec on the main website. But anyway, everything is here, everything. In fact, there's sort of one link, it says roadmap, and that's got the videoed lectures, the homeworks, the lecture outlines, the PDF, the slides, the interactive labs, how to get to the server, everything is there. I try to make it complete. And if you have problems with it, tell me. I mean, I put it together. That doesn't mean I'm using it. You're using it. So you should tell me how you want it to work. So this flipped course, right? Regular course, I would stand here like this and pontificate, speak at you. And I've done this for years past. I'm incredibly uncomfortable because next week I'm not going to do that. And we're going to come in here and we're going to work together on problems. I will sit down. We will discuss the online lectures, the videos you should watch. Bring all your questions. Basically free form. You should be using this so you understand. I'll show you how to use the server, the Sage server, and how to do homeworks. We'll go through interactive labs that show you the basic tools, constructions you need to do the homeworks. We'll work example homework problems together. I'm really hoping that basically everyone turns in perfect homeworks at this. I'm willing to go through everything. In fact, if you'd like, you can work in groups together on the homeworks. We'll deal with the kind of details of this starting next week, but I'm very flexible to see what you'd like to do with this. I have some suggestions, and I have certainly plenty of material when we show up here that we can work through problems, discuss issues. There's some readings for next week which are listed online. So the actual class meetings are going to be for problem solving and discussion. I will occasionally just insist that I show you my new fancy interactive lab on the browser so you can go play with it. Simulations, symbolic calculations, numerical calculations, all sorts of things, even visualization. I would strongly urge you to bring your laptops to the course meetings because we'll be working in the browser. So what's online? All the lecture videos. So again, today is anomalous. From last year, I have 3 or 4 lectures I have to redo like this one. And so on those days as they come up, I will just give a regular lecture and record it. But basically, they're all online. And every week, I'm going to be putting them up there, updating things. The readings are listed there, and also how you get access to the Sage, or Computation Mechanics in Python server, where we have all the homework assignments are there. That's how you hand them in, and also the interactive labs that get you up to speed. Yeah.
The lecture video only accessible by registered students. How about students who just auditing the class?
Oh, the videos. It's all that website URL I put up there. That's publicly available. Right. If you're just auditing, you don't get access to the Sage server. That's actual computational resources and takes a lot of management. So, and I have a little. Maybe you saw there is a little plea to not audit, rather to enroll. So, but that's fine. I mean, I don't mind. I don't mind people sitting on the lectures and yeah.
So on the readings, will that be the 2 textbooks that are listed for this course?
Yes, yes. Mm-hmm. Well, and then there's also a series of articles. So initially, I pretty much this quarter will be going through this nonlinear dynamics book and the information theory book. So it'll be chapters to read or parts of chapters to read and exercises from the book. But then as we move more towards the end of this quarter and start extending information theory to really apply to complex systems, that's more the research frontier, and so there'll be research articles we'll be reading. Again, so right, the two books. So Steve Strogat's book on nonlinear dynamics and chaos. I supplement this a little bit with some additional topics on chaos and also on this instrumentation notion called symbolic dynamics. That's not part of here, but that'll be in the lectures. And then the second half of the winter quarter will be from this Elements of Information Theory by Tom Cover and Jay Thomas. Nice book, a bit big. And then this list of articles is here. So you'll see that. There are links on the page to these articles and so on. Pretty much everything is online, as best as I could. PDFs of the articles and so on. And then the sort of lecture notes, slides, raw slides, but also slides with voiceover, and the videos of the lectures are all there. So whichever format you prefer. Seems like most people just like the video lectures to go back and forth. This is not a course on programming, but if you have some familiarity with programming, it'll be a big help. But we'll help you get started. And that's, I guess, one of the benefits of the flipped class. We can spend more time with you getting used to some of the programming environment. Again, the focus is not programming and algorithms. Many of the homeworks and labs have helper code that we've written, so you just use a high-level function because I want you to focus on the concept. I don't want you to write the differential equation solver. I want you to see the solutions and understand their geometry, and so that's how the homeworks are set up. So I guess we'll just have to sort of see. Usually there's a very wide diversity of programming talents. Some people are like, oh yeah, I can do that. I know. The website has suggestions for tools and development. The SAGE system has a very nice tutorial for how to use it. So, but that's all explained when you go to the SAGE server. So the website, don't expect to just scan the website quickly. Some of the pages have lots of information on them. So kind of read through the website, click around a bit to figure things out.
I was going to ask if we need any libraries installed on our local laptops or whether everything's cleared up.
You know, I used to teach a computational physics class and also this class where we had everyone install on their own operating system the libraries we use and the homeworks and stuff. It was just a mess. So it's a real boon to have everything in a browser. It's just unbelievable. We control the source, I can update things, and it's all very uniform. There are a few glitches every once in a while, but it's not that big a problem. And that becomes particularly important when we move into the last half of winter and all the spring. We'll be using this, our group's own software package called computational mechanics in Python. How you calculate entropy rates and eigenvalues and all that kind of stuff all gets packaged up, and it's very easy to use. So again, this is the URL that takes you to the SAGE Campy server. All the labs, interactive labs, preparation for the homeworks, are just things that expand on or give demonstrations that go along with the lectures up there. The homework assignments will show up there on Tuesday, and they all run in a browser. I'm willing to sort of help with Firefox, Chrome, and Safari browsers. Internet Explorer. Sorry, yeah. I didn't appreciate what a wild world the web was until you start making your own pages, and then you look at different browsers, how they get formatted, and it's just, anyway. Much better these days, generally, than it was before, so that's great. And then underneath SAGE, the main language is Python. It's a sort of modern, interpreted language, very flexible. If you've done Mathematica or MATLAB, very similar to R, which is statistical analysis, but it's a real programming language, unlike all of those. People do many different kinds of things in Python because it's a real language. So we can do our computational science methods, integrate differential equations, solve linear algebra problems, but you can also go on the net and grab data. You can start up databases and run databases from Python, do operating system programming. You can do everything here. It's nice, nicely structured language, and it has great libraries. So, and those basically all get inherited in this SAGE package that runs in the browser. So there's just nothing you have to install. Yay. We have to worry about it. I have to worry about it. But okay, so readings to do. So this is all part of your figuring out where stuff is on the class website. Okay, so computational mechanics reader article. So this is for next week. I want you to go read this article by the Polish science fiction writer Stanislaw Lem, who just passed away 5 or 6 years ago. As I don't like science fiction, but Lem, out of many, many science fiction writers, actually understands probability theory and information theory. So his things are very, I love them. They're very tongue-in-cheek, very kind of ironic, very funny. So read his article, Odds, and you'll see on this page, the CMR Computational Mechanics Reader page, there'll be, in the list, there'll be a tag called Odds. And then you can just click on that and there'll be a PDF. And also just to give you some little heads up on what this deterministic chaos is, nonlinear dynamics and so on. There's a short article that a number of grad students and I, back when we were way back, grad students at Santa Cruz, we wrote an article on chaos that appeared in Scientific American. Again, these are just short, fun articles that give you a little bit of information, get you oriented a bit, and we'll talk about them because we'll have more time in the class meetings to discuss these things. And then for the technical reading, look at the Strogatz book, Nonlinear Dynamics and Chaos, and look at chapters 1 and 2. Chapter 1 is high level, half a dozen pages. Chapter 2 starts to get into looking at one-dimensional differential equations. Okay, so those are the assignments. And again, all these slides appear over on the course website under lectures or the roadmap. You can get to these slides. So if you don't even have to write down what these are. Little thing, so there's no class meeting on Thursday. I have a large meeting with about 60 people starting up this large project on molecular information processing that I have to run on Thursday. So I'll be a little busy. So, so the next lecture meeting time is Tuesday. And so you should do those readings, come ready with questions, any questions from this lecture. There is a video for Thursday, so you should look at that video, and we can discuss that next Tuesday. Now, if you want to get some hint, maybe some of you are thinking, well, do I want to stick through this whole 2-quarter thing? How to say this? I think, but I'm prejudiced, that the most interesting ideas, most interesting mathematics and physics occur in the spring quarter. This whole issue of intrinsic representation, information storage. So there's a recent review that I wrote in Nature Physics, January 2012. Again, this is linked on the course website. So you might, and it's just 6 or 8 pages, it kind of gives you an orientation, this kind of larger picture of what we'll be doing if you're curious about what's going to happen in the spring. Okay, and there's homework. Homework gets assigned every Tuesday, and it's due a week later. For homework 0, I want you to think over the next week, possibly you're sort of noodling around doing whatever you're doing on Saturday and Sunday, about 3 examples of unpredictability. So this is a narrative exercise. I want you to come up with 3 examples of unpredictability that you experience. Sometime between now and next Tuesday. And then for each of these, answer these questions. So where did you encounter it? What was kind of interaction did you have with it? Why did you think it was unpredictable? I'm kind of curious. What effect did its unpredictability have on you? Did it materially affect you? What aspects would you expect to predict? You know, if something's unpredictable, it doesn't mean it's utterly unpredictable. Maybe there's some things that are predictable, and then how would you model it? And what I have in mind here is just sort of write a paragraph that addresses these questions for each one of the 3 examples. And then when we get together on Tuesday, we'll talk about it. Part of what I want to do here is to kind of engage you intuitively in these ideas of what's unpredictable, what's predictable, what's order, and what do we do when we think about modeling something. In fact, it's kind of a funny thing especially at a research university where we have these graduate programs. There really aren't courses on modeling, which is a really important thing, right? How do you go from staring at the world and seeing something to building a model? very often the courses we take are very siloed. Oh, you're going to do solid state physics, and there's a whole range of things that we can think about, basically using models that people have already invented. But how do you start to model something that is kind of out of your, kind of disciplinary silo? So as we discuss this next week, maybe we can sort of deal with that. So, okay, so that's actually all I had to say. Again, so happy to answer any questions. We can, at this point, pretend we're doing the flip course. You can ask me technical things, non-technical things.